Hello, everyone, and welcome to the 10th Annual 2021 Student Research Symposium. My name is David Cox, and I'm the Director of the Skene Library and the OSL and the SRS program. The SRS is an annual campus-wide event that provides both undergraduate and graduate students the opportunity to present their research in a variety of formats. It could come in poster sessions like today, oral presentations, and 3-minute speech competitions. If you attended yesterday's events, we hope you found them informative, educational, as well as fun. We have a few more events today and tomorrow that we hope that you will consider attending as well, and we'll give you some more information on that later in today's session. Thank you for joining us today for this third poster session. The SRS is grateful to Tech faculty member Professor Matthew Johnson from the class department and former Tech employee and Tech alum Liz Lyons for their assistance today. Dr. Johnson will be moderating today's session, and Ms. Lyons, with the help of SRS staff members, will be assisting with the tech. Now, during normal times, the SRS would take place in person on our beautiful New Mexico Tech campus. We're still at the New Mexico Tech campus, and it's still beautiful, but because of COVID-19, we greet you in this virtual world for our second virtual type of presentation of the Student Research Symposium. This session is a poster session. Several New Mexico Tech students will have the opportunity to present their research to you, and you'll be able to ask questions. In a moment, Dr. Johnson will start things off, but first, a brief word from an SRS staff member.
Thank you, Dr. Cox, and thank you everyone for being here today. So before we get started, I just want to put Dr. Cox on the spot and wish him a very happy birthday.
Oh, thank you. SRS seems to be my birthday time every year, so it's what we get. So you all at your poster celebrations are celebrating my birthday. How's that? Yep. Okay. And I'm glad to hear you.
All right, everyone. So we have a lot to cover. So this is how today's session is going to unfold. So each student or group is going to give a brief presentation based on their poster, and then the moderator is going to facilitate questions from the audience. So during the presentations, all of you will be muted so that way there's no background noise and no interruptions. And when the time comes for the Q&A, you'll be able to unmute yourselves and ask questions. And of course, the chat box is going to remain open during the entire session. And if you need any technical assistance, please feel free to send a direct message to Liz Lyons or an SRS staff member. So for ease of use and access, the moderators, volunteers, and presenters are going to be listed at the top of the participant list. So a couple of things to get started. We hope there are no technical issues or any issues with internet access today, but if we do somehow experience a problem, please just be patient as we try to work through it. If some sort of power outage or a major event happens, we'll be in contact with you via email, apart from the meeting if you've provided one to us. So one suggestion for the session itself, you might want to change your settings to speaker view, and that'll make the visuals and presenters be the main thing on your screen. From time to time, we will also be posting the link to the poster gallery in the chat box, so that way you can take a look at the posters throughout the session. We'll also be posting a link to the evaluation so that you can evaluate the presenters today. Please fill that out as often as you're comfortable with. I'm sure our presenters would appreciate any feedback they can get, and you'll need to fill out a separate evaluation form for each poster or group. So thank you again for joining us today. Dr. Johnson, you can kick it off.
All right, well, once again, welcome everyone. Good morning, and thank you for joining us today for Poster Session 3. We have 15 presenters presenting 12 posters during the session. Please keep an eye on the chat to get the link so that you can take a look at each poster. The presenters are here with us live and will be available for questions. So what we'll do is we'll have one presenter or presenters present, and then we'll have questions, and then we'll move on to the next one. We can also use chat for questions, I believe, if you would prefer that. So let's start by introducing our presenters. So what I'll do is I'll introduce each presenter or presenters and the title of their poster, and then I'll let them speak, and then we'll do the Q&A, and then we'll move on to the next one. So our first group of presenters is Grace Tenorio, Marco Losoy, Justice Ingstrom, and Isaac Edelman. And the title of their poster is Guided Wave-Based System for Cure Monitoring of Composites Using Piezoelectric Discs and Fiber Bragg Gratings of Formula One Vehicles.
Hi, so this is Justice Ingstrom speaking. And so should I go ahead and I guess present the poster?
Yes, please.
Okay, definitely. So we did this work a part of the NASA 2021 MIDIC competition, which in essence, we took an NASA IP out of a list that they had given us. And then we're to come up with a spin-off idea that can kind of take the idea to the next level and kind of commercialize it. So the NASA IP was the guided wave-based system for cure monitoring of composites using piezoelectric fiber Bragg gratings. And our spin-off idea was to make, I guess, embedded sensors within carbon fiber sections of vehicles. So figure 1 there, you see a diagram of a Formula One style monocoque. So monocoques in, I guess, in Formula One, but in automotive, aerospace, and the boat industry is a structure that is both structural and also kind of like the outer skin. So a common vehicle, you might have a body and then you have a skin on top of it, and so this is all in one. And so this would allow for complete life cycle monitoring of the system, where when you're curing the composites of the monocoque, you're able to make sure that it's done well and done properly. And then when you go on to use the monocoque itself, then if you have impacts or things like that, you're able to use the embedded fibers to tell the stress of the material, monitor temperature. It has, I guess, many huge benefits. It's immune to electromagnetic radiation. It's immune to regular radiation. It's explosive resistant, and so that was like the main push for this competition. So you'll notice a lot of it's more, I guess, a little bit business related, and because it's a competition kind of related to that. But that's the product itself. And so all of this will be communicated to an onboard computer that then can store the data or send it off to a communication bus. And the big need for this type of product is currently, if you were to have a carbon fiber monocoque, you'll have separate equipment and technicians that are there during the manufacturing process for cure monitoring. And you also have separate technicians that if you incur damage, you have to fix. And then, fixing it also is an entire thing. So this kind of eliminates many aspects of the process. And the huge push for this really is the fact that each 10% reduction in gross vehicle weight increases fuel economy by 8%. So for electric vehicles and I guess even gas-driven vehicles, you're able to increase range significantly through the introduction of carbon fiber. And this type of technology would reduce the barriers to entry of carbon fiber in, I guess, any industry that really uses a carbon fiber monocoque. Thank you.
And at this point, we can take questions from the audience. So please feel free to ask. And I suppose that I can begin. My question has to do with if this improves fuel economy, what are the cost barriers? What is the reason why it's so much more expensive to use these monocoque to make the exterior where it's all one piece, as opposed to the way they do it for sort of like the car I drive, for example?
Okay, so I guess a good answer to that is if your modern car has a side impact, then you have to just replace one of the panels that are bolted to the frame. But for a monocoque, if you have an impact, then you might have to check the entire frame because it's all just one big piece, and you're not really going to know how the damage propagates unless you inspect it and check it. And so this allows for instantaneous checking of all aspects of it, so you know exactly which panels would be affected and which ones need to be replaced. And then when you replace them, you can also real time have monitoring of how the fix is going and if it was fixed properly. So it kind of reduces a lot of those barriers that modern cars are able to kind of fix by default. And to answer the question of Joaquin in the chat, so that is exactly how it is. So while you're kind of laying the layers of the carbon fiber, you would embed the sensors within it. And then those all would terminate at the end of the section, so then they can go to the onboard computer.
Is there a depth of insertion, you know, where the sensors work better than others? So like if you embed it, you know, 4 millimeters below the surface of the carbon fiber or 10 millimeters below the surface of carbon fiber, is there kind of a trade-off in embedding that at certain depth?
That's a good question, and I guess I can't answer off the top of my head, but I imagine there might be a linear relationship. Especially, you'd probably want the sensor to be in the center of the material, because I guess it's going to kind of change how things kind of lay out if you're, I guess if you have the sensor offset within the material or the carbon fiber stack.
Cool, thank you.
Thank you.
Are there any additional questions? Well, at this point, we can move on to the next poster. Thank you, everyone. Thank you, Justice, Grace, Marco, and Isaac. We can use the icon of celebration of our choice, our reaction in Zoom. I prefer the party icon. So our next poster presenter is Nicholas Harrison. And the title of his poster is A Study of Abandoned Mine Lands in New Mexico.
Okay, so thank you, everybody. I will be talking about hazardous stuff, so you weren't too far the mark, Matt. Landmines are dangerous too, but I'm going to be talking about abandoned mine lands, which are dangerous in themselves. So I'll start out by talking about, well, what are they and why do they matter? Abandoned mine lands, or AML, are lands that were excavated and left unreclaimed, and where there's no individual or company who has reclamation responsibility and there's no closure plan in effect. Sometimes that can be because the operator just walked away as soon as the ore was exhausted. Other times it's because the mine was opened before the 1970s when they passed a law which said that you have to have a closure plan in effect when you begin a mine. So these excavations are caved in or sealed, and they're places where there's no further mining intended in the future. They occur on lands with a variety of ownership, like federal, state, private, or tribal lands. And to avoid confusion, there are some other terms for them which may be used interchangeably. They're also called inactive mines, legacy mines, or orphaned mines. And this map here, I don't know if you can see my cursor. So I guess these are the districts. Okay, yeah, let's see. Maybe if I can you enable cursor sharing, Matt? Or if
I can give you.
Cursor.
Sure,
Okay.
yeah, I could do that or give you remote control.
Yeah, that's what I was wondering. I mean, if you can't, that's fine.
There you go. You should be able to remote control now.
All right, you can all see it.
Yep, we sure can.
All right. So this is a map of the mining districts that were studied in this survey. I will point out a few of note. There is the North Magdalena district right here, number 6, where my co-author Marcus focused on for his master's thesis. There is the Gainas Mountains, where I did a lot of my work specifically. And then there's the Rosedale district, which John, my other co-author, focused on for his master's thesis. And I do owe a debt of gratitude to my co-authors who unfortunately are not here today and or have moved on, but obviously I could not have done all these sites without their help. So what did we do at these sites? Well, to begin with, we go out to various mines within these districts, and we take inventory of them. We have a special inventory form which we use to classify each mine. So we talk about things like what kind of vegetation is present there, whether there's any wildlife like owls or bats living in the mine shaft. And then we take, once we do that, we take measurements of the mine. So we measure the depth of the shaft, either with a surveying tape, or if it's too deep to use that, then we throw a rock down there. And if we don't hear it bounce, we assume that it's more than 50 feet deep. So once we take those measurements and measure the width and depth of the shaft, we collect samples from the waste rock piles, which are the piles of rock which you'll see at the side of abandoned mine shafts, where they throw all the stuff out when they excavate the mine. We collect composite dump samples of soil from those from the waste rock piles, and then we take those back to the Economic Geology Lab in the Bureau of Geology, where we run a series of analyses on them. Those analyses include paste pH analysis to determine the acidity of the composite of the waste rock piles, to determine the risk of acid rock drainage and other chemical hazards. We also conduct soil petrography to determine the mineralogy of the samples. And as for the results that we've gotten from this study, here's just this table here has just a bit of some of our results. Obviously, there's a lot more chemical analysis that we get from these results, but here are just a few. Mainly, we're looking at sulfur content of these mines. And as you can see, some of them are a little bit higher than the other ones. So what are some of the potential impacts associated with abandoned mines? Well, like I said, there's the chemical hazard from acid rock drainage, and sometimes there's also heavy metal contamination. And there's also the physical hazards. We don't want people to fall into abandoned mine shafts and die, which unfortunately does sometimes happen. And most of all, there are the unknown unknowns. A lot of these sites have not been inventoried, so we have no idea what kind of hazards might be lurking there. So in addition to the works that the work we get ourselves, do ourselves at the Bureau, we also send some of these samples off to ALS Lab Services in Reno, Nevada for whole rock geochemistry. And that's where we get more bulk geochemistry analysis. And we plot our results on this ARD classification plot according to the chemical content and of these samples and the resulting classification of how dangerous they are, which is how high their levels of acid rock drainage are. And once we've concluded all, and here you can see the formulae we use for calculating that. And then once we've completed all these analyses, we classify the hazard rankings of each of these abandoned mine sites according to the classification developed by the NOAMI of Canada. So these classifications range from R, which is remediated, where the closure plan hasn't put into effect, and EMNRD has gone in there and done something like sealed off the shaft or done whatever chemical remediation necessary to reclaim the site. O, where information is not available, like we know it exists, but we have not been able to get out there to do inventory. D, which is a site where there is no hazards, so like no acid rock drainage and no shafts for anybody to fall into. C is a site with public safety concerns, but no public health or environmental concerns. So like a shaft, but no acid rock, an open shaft, but no acid rock drainage. B is a site with limited potential to cause environmental concerns, but not much for public health and safety. So that's the opposite, which is acid rock drainage, but no open shafts for people to fall into. A is a site with potential to cause environmental and public health, so acid rock drainage and open shafts. And we found that in the course of doing this, that some mines do have the potential to generate acid rock drainage, especially those with lower amounts of calcite and other acid neutralizing minerals, as well as higher amounts of sulfur, and also higher concentrations of pyrite, which is a sulfide mineral. And I'm ready for questions, and I see that there's already one in the chat. Let me just stop remote control. And so the current best practices for mitigating ARD, well, it's to be honest, what we are doing is mostly focused on figuring out where ARD exists. Once we figure out that it does exist, we turn to the Energy, Minerals, and Natural Resource Department, EMNRD, of the state of New Mexico, and they're the ones that go in there and do the actual remediation. I'm afraid I can't answer that question. Any others?
So I'm guessing just a great big fence around these areas is not really going to do it, huh?
Well, I mean, they do put fences around some of them, but of course people are curious and they can climb over fences. Certainly putting boards or other covers over open shafts does help.
But I'm assuming that you're trying to make something a little more inclusive, let us say, to restrict people. I happen to remember being a 6-year-old having fun in the coal mine shafts that weren't far from my house. And it doesn't make any difference how old you are. A lot of people are drawn to those types of places, especially the issue with the acid concerns I see. So do you have any future way of maybe projecting places that will need a specialized type of care?
Well, that is another long-term goal of the project, is to determine whether there's a correlation between the type of deposit that the mine is established in, like for instance, volcanic sulfides or fluorite veins or Great Plains margin, which
Right.
And whether there's any correlation between the deposit type and the potential for ARD.
Yeah. Thanks.
Nicholas, I'm just wondering, during your research, have you encountered anything that was particularly interesting or unexpected?
Well, I did. There was one shaft in Rosedale where I did find a bat living in one of the shafts. Fortunately, he didn't come out of the shaft. He'd been sleeping in there, and when I tossed in the rock to measure the depth, that woke him up, and I saw him flying around in there, but he didn't come out and attack me or anything.
So we have another question in the chat.
Yes.
Would the EPA become involved in the remediation?
They haven't really been involved in this project, at least not directly, although they do issue guidelines on this type of thing that we do try to follow.
So
what type of, I'm sorry, what type of guidelines? Like, do they set certain thresholds with which some of these things being present would be a concern?
Yes, they do. Unfortunately, I don't recall any details of that off the top of my head, but yes, they do establish thresholds for what they consider to be hazardous at what levels.
Okay, thank you.
So with the ARD, I'm assuming this would be affecting the groundwater.
Yes, it does affect groundwater.
Well, if there are no additional questions, we can once again give our favorite Zoom reaction and we'll move on to the next presentation. Thank you, Nicholas, for the fascinating discussion of mine lands. Our next presenter is Thomas Gaudin, and the title of his poster is Investigating Mass Transfer in Symbiotic Stars Using the Cara Optical Interferometry Array.
Hi, everyone. My name is Thomas. I'm a first-year master's student in the physics department. I will be talking about this research project that I started with Dr. Ryan Norris this semester, investigating symbiotic stars. So symbiotic stars are a type of interacting binary star system that consists of a red giant star and typically a white dwarf companion. These systems are characterized by long orbital periods, a relatively wide separation between the binary components, and a dense circumstellar medium or cloud of gas and dust that surrounds both stars. Symbiotic stars are currently very poorly understood, but learning more about them is crucial to improving our understanding of the late stages of binary stellar evolution. Now, as we can see from the artist's representation in the top center of our screen, the red giant in a symbiotic star system is not spherically symmetric. Instead, its radius is larger at its equator, pointing towards the white dwarf, than it is at its pole. Now, this radial asymmetry or teardrop shape is what we call a Roche lobe. And this Roche lobe indicates the presence of mass transfer as mass is transferred from giant to dwarf due to gravitational interaction. Now, investigating mass transfer in symbiotic stars is crucial to informing our expectations of how these systems will evolve with time. Research suggests that the best way to investigate mass transfer in these systems is to directly measure the geometry of the red giant. Once we know the radius of the giant at the giant's equator and at the pole, then we can directly calculate the rate of mass transfer. These measurements are only possible using optical interferometers, which use several telescopes to simultaneously observe the same object, allowing the study of small objects such as individual stars. However, very few studies have used optical interferometers for this purpose. To date, all published work on this topic has made use of the Very Large Telescope Interferometer, which is a 4-telescope array in the Southern Hemisphere. As we can see in the bottom left, VLTI was used to observe systems such as SS-LEP, which we see here observed in 3 different orbital configurations. VLTI has been used to some degree of success to perform imaging, but these studies left open questions about the geometry of the observed systems that we can only answer by observing with a higher resolution interferometer. This is why we have proposed to use the Cara array, which is currently the largest optical interferometer in the world, to observe several symbiotic star systems. To date, no published work has used Cara for this purpose. So with Cara's unparalleled resolution, we hope to achieve the clearest picture yet of mass transfer in symbiotic star systems. We're currently in the proposal stages, but we have managed to simulate observations of each target system using code packages developed by our collaborators at Georgia State University. These code packages use known parameters of the system to build a model of the expected asymmetry, which we then use to inform simulated observations on our proposed observing nights. Once we have simulated an observation, we can then create a reconstructed image of our target stars, as we see on the right-hand bottom side of the screen with target star BD Cam. As we can see in our reconstructed image of BD Cam, we have a clearly larger radius at its equator than at the pole, indicating high rates of mass transfer. These reconstructed images clearly demonstrate the ability of Cara to resolve the giants and symbiotic systems well enough to allow us to measure radial asymmetry and therefore directly calculate mass transfer rates. Now, hopefully, this will lead to successful observations when it comes time to observe our systems in fall 2021 semester. Does anyone have any questions?
Yeah, so why? Why are
So
we doing this? Why is it important?
So symbiotic stars are connected to several late-stage stellar objects. So we believe that they're connected to important objects such as symbiotic X-ray binary systems, type 1a supernovae, variable stars, and even planetary nebulae. So if we can figure out how these systems will evolve with time and figure out how fast mass is transferring, we can figure out how the white dwarf will grow and figure out what these systems might evolve into or what we expect to happen as these systems progress.
So they're kind of like a baseline for the development of other astral bodies.
Yes, correct.
Cool. Awesome.
So we have a question. Do we hope to observe other types of binary star systems other than red giants and white dwarfs? Some of the proposed systems, one of them actually is the SS LEP system, which we see down in the bottom left-hand corner. That one doesn't actually have a white dwarf companion to the red giant. Instead, it has a larger star, but that's pretty rare in symbiotic systems. We expect to mostly have white dwarfs. We chose red giant systems specifically because red giants are large stars that can very easily be observed using an optical interferometer, which needs a star that's relatively close and relatively large for us to be able to directly resolve it through imaging. They're also very bright in the near infrared, which is the wavelength we hope to observe in.
And Thomas, I believe Michelle has another question. She has her hand raised. So Michelle.
Hi, Thomas. I was wondering if in your studies you were able to figure out how many of these might be available to something like MROI in the future, say down to 10th or 12th magnitude in the infrared?
There are approximately 100 currently available to Chara. I think in my studies I've seen maybe that number could possibly double if we can get that once MROI is online, and we'll have longer baselines than Chara. So hopefully the symbiotic stars will become a good target for MROI once it comes online in the future.
Thanks.
And how far out are we from MRI actually being moderately usable?
So Chara currently has 6 telescopes in the array. Once MROI has more telescopes with a larger separation between widest scopes, Michelle probably is better equipped to answer this than me. It will be functionally better at observing these than Chara, but I think that's still quite a long ways away.
It's entirely funding dependent, Michael.
Yeah. Okay. I was hoping for the best, really. I was hoping.
Yeah, well, write a check and that'll help. So.
Ooh, I could write you a check, but I wouldn't try and cash it.
Well, thank you, Thomas, for the fascinating poster. We will move on to our next presenter. Our next presenter is Cameron Stephenson, and the title of their poster is Mitochondrial Function Across Sexual and Asexual Lineages of a Freshwater Snail.
Hello, my name is Cameron Stephenson, and like Dr. Johnson just said, the title of my project is Mitochondrial Function Across Sexual and Asexual Lineages of a Freshwater Snail. Our main objective currently for our project is to design and optimize a series of functional assays to determine how several factors, including mitochondrial background, ploidy, and mode of reproduction impact mitochondrial function. And the freshwater snail P. anthropoderum that we use in our lab makes a good model organism for our purposes because it includes both sexual and asexual lineages, where the sexuals are diploids and the asexual individuals are either triploids or tetraploids, allowing for direct comparisons between things like mode of reproduction and ploidy. And as seen in my poster here, the functional assay that we started with was a behavioral assay that looked at the writing times, or essentially the time it takes a snail to move from the back of its shell to right side up, and in response to heat stress. And the reason we looked at these writing times was because for the snails, flipping themselves over is very energetically expensive and hard to do. And so if they don't have enough energy, they can't do it. And therefore it can be a pretty good indicator of their mitochondrial function. And our initial data at the bottom of starting at the bottom of the middle column here, showed that the ideal temperature where these snails were happiest and most active was 15 degrees Celsius, while 25 degrees Celsius was the point of stress where a majority of the snails failed to right themselves by the 5-minute cutoff period we had. Our data also showed that at this 15-degree temperature point, the tetraploids appeared to have faster writing times than both the diploids and triploids overall, which indicates that ploidy may have a strong relationship with mitochondrial expression and function. And Our future goals for this project are to, first off, include a 20-degree temperature point in this behavioral assay we did, because currently there's a little bit of a gap in between 15 and 25, and we're curious what happens there. And also, we are hoping to move on to developing a couple different, not behavioral assays, a couple different functional assays, including things like just mitochondrial function, ATP production, oxygen consumption. Yeah, and that's about it. So does anyone have any questions?
So we have a question in chat from Joaquin, who asks, what is ploidy?
Okay, so ploidy is just, so some individuals are polyploidy, so it essentially means that they have more than one copy of their chromosomes in their genome. So like a diploid has 2 copies of a chromosome and a triploid has 3 copies of that chromosome.
I guess I could ask a follow-up question. So how does, I'm trying to visualize this, how different numbers of copies of chromosomes occur in asexual and sexual reproduction. So could you, I guess, explain how the different modes of reproduction lead to different ploidies, I guess?
Yes, it's kind of the reverse, where the polyploidy event, I'm not exactly sure why, but it will usually result in different modes of reproduction. Essentially, they lose the ability to reproduce sexually once they have too high of a level of ploidy. And I think there was another question on how the ploidy affects the writing time, and that's kind of what we're trying to figure out, because we are just trying to see if the level of ploidy does have an effect on mitochondrial function or writing times, which is a measure of mitochondrial function. And some of the possible reasons we think it could are that with this extra chromosomes, it leads to potentially higher expression of the mitochondria. And therefore, if the organism has a higher number of mitochondria than, say, an organism with lower ploidy, it might therefore be better at processing energy and ATP, so that it would have more energy and have better function overall.
I guess I have one more sort of silly question. How does a snail write itself?
It is actually very interesting. I get to see them do it under the microscope. Pretty much they have to like try to stretch their neck and head out of their shell and like flip themselves over.
Well, thank you, Cameron, for the fascinating presentation. I got a feel for these low energy snails at temperatures outside of their preferred temperature. And with that, we'll celebrate your presentation and move on to the next presenter. Our next presenter is Savannah Bradley, and the title of her poster is Biomimetic and Bio-Inspired Anti-Predator Drones.
Thank you. So I'm Savannah Bradley. I'm an undergraduate student in the mechanical engineering department, and I am currently working on research with Dr. Mustafa Hassanalian on biomimetic and bio-inspired anti-predator drones. So drones have about 200 applications, actually probably even more. But my focus is on drones in the defense industry. Drones in the defense industry can be used for multiple things, whether that's military, border patrol, or general surveillance. And these drones are susceptible to a lot of different predators, because especially with military drones, other countries or other predators, if you will, are wanting to get rid of these drones. So there's 4 predator mechanisms that I've been studying, looking at detection, tracking, targeting, and attacking. So detection is trying to find that drone, and there's multiple ways of going about that. There is acoustic sensing, radar, thermal imaging, and visual. And in the first column, the picture on the hand side shows thermal imaging is one of the detection methods. And drones are tracked, targeted to ensure the drone predator acts to attack. And impacts to the left, third,
Savannah, your audio, there we go.
Yeah, thank you. So picture left is often our rhythms are able to the mechanism which is other animal and which is a drone that they're actually avoid these predator attacks.
Savannah, we're continuing to have some audio difficulties,
I need to see if
Savannah, this is Sarah. If you'd like to maybe sign out and sign back in, we can move on to the next poster and we can come back to you.
Okay. Sorry about that. I'm having some internet issues on my end.
That's okay.
Happens to the best of us.
Take a deep breath, turn it off and on again, and we'll see you in a few minutes. But we'll move on to 134.
Sounds good.
Okay.
Okay, so we'll come back to Savannah. Our next presenter is Dana Milani Neal, and the title of their poster is Developing the Atmospheric Dispersion Correctors for the Magdalena Ridge Observatory Interferometer.
Good morning, everyone. Hopefully you can hear me okay. I was also having some internet issues a few posters ago and got kicked out of Zoom and brought back on. So I understand the internet struggle. As was mentioned, my project is developing the atmospheric dispersion correctors for the Magdalena Ridge Observatory Interferometer. And since that's a bit of a mouthful, I will be referring to it by its acronym, the MROI. To introduce those of you who are not particularly familiar with interferometers, an interferometer is essentially an array of telescopes. And when you have multiple telescopes along baselines of this array, they essentially can act together as one very large array. So with the MROI, we are hoping to have 10 telescopes on the array, and they will range in baselines from 7.8 to 340 meters, which is very, very amazing. With this setup, the MROI will be able to reach resolution capabilities greater than 100 times the resolution of the Hubble Space Telescope. So lots of fun and exciting science is going to come out of the MROI. The MROI will be operating at wavelengths from 0.6 to 2.4 microns. So this is an optical and near infrared interferometer. My project is to develop the atmospheric dispersion correctors, which I will refer to as the ADC. And the reason why these correctors, the ADCs, are important is because if you take a look at figure 2 in the left-hand panel, sorry, it's a little difficult virtually to see, but if you can see, we have rays of light coming from a target, and in the upper panel of that figure, this is occurring in the vacuum of space. And as this light travels and is impeded on the Earth's atmosphere, the Earth's atmosphere has a refraction index. And essentially what happens is when light travels from the medium of space into the Earth's atmosphere, different wavelengths of that light will be refracted at different angles. And so as this light travels to the telescope, shown in the figure, we see that different wavelengths will arrive at different spatial positionings on the telescope. And this eventually becomes translated. So for the MROI system, the light will be relayed along beam delay lines. And so when there are spatial differences being propagated through these delay lines, the differences will become extremely amplified. And when all of the light from each telescope is being focused onto a detector, this creates a huge problem because we will have different wavelengths, which many people find a little easier to interpret as color. They will arrive at different spaces or physical positionings on the detector, or possibly even not on the detector. And so to correct for this, this unfortunate phenomenon, what we will be doing is we will be implementing an ADC on each telescope. And an ADC in this case is going to be comprised of 2 glass prisms, and each prism is comprised of 2 different types of glasses. So if you take a look at the bottom of the left-hand panel in figure 3, you can see an illustration of the ADC in its entirety, as well as how it essentially corrects for the spatial differences of wavelengths of light. And the way that we have been determining the optimal solution for the ADC is to use a tool that has been designed by a PhD student at the University of Portugal. And he wrote scripts in Python to create this tool that will sort through the infinite amount of glasses that exist and produce the pairings as well as the angles of the prism and the size of the glasses necessary for us to achieve the performance requirements that MROI needs to meet. So a little about the selection procedure to use this tool. We give the tool various parameters. Some of these parameters are fixed, meaning that it's non-negotiable to to be operating at a value that is not this parameter. So for example, our minimum wavelength is 0.6 microns and the maximum is 2.4, and we need it to operate at all wavelengths within this range. There are upper limit parameters, meaning that the optimal value reached within up to that point would be acceptable. And we have lower limit parameters, meaning that we cannot fall under or fall short of this requirement. So for example, the ADC transmission, or how much light emerges after traveling through the ADC, we currently have set to 90%. And so that would mean that we would be losing 10% of the light that is incident upon the ADC. So to give an example of some of the results produced by this tool, you'll see in the middle right panel that we have 4 graphs. So the top 2 graphs are for the combination of 2 glasses called SFPM2 and NPK52A. And a disclaimer, I do not name these glasses. There are conventions that indicate what type of glass it is, as well as very interestingly, if it is quote, quote, environmentally friendly, which means that it does not contain lead, or arsenic. And so the left graph, which is figure 4, shows the residuals. And so these residuals are essentially, without getting too deep into this, when wavelengths of light are incident upon a detector, they create what's called an airy disk pattern. And so a residual is referring to the difference in location or position of these airy disks for each wavelength of light. So if there were 0 residuals, that would mean that all wavelengths of light are incident on the same location on the detector. So the higher your residuals are, the more spatially different these wavelengths of light are. The right side figure, figure 5, is a transmission plot. And so sorry that it's very small here, but we see that the transmission remains above 98.25%. In other words, we are only losing 1.75%, percent of the amount of light that is entering the system. And we are also given other characteristics of the glass, such as the center thickness and the prism angle. And so the 2 results displayed here are 2 of very, very many iterations of running this tool. And our hope is to continuously run this tool to change our parameters and examine the results until we fully optimize a solution that will be feasible economically, because 10 of these would need to be made, as well as mechanically employable. So we would want them to fit within our space parameters, as well as be mountable. So if the glass is too fragile, too thin, too big, it would be very difficult to place in the system. And we want it to make sure that we do ultimately meet our requirements for performance. So for some acknowledgements, I'd like to thank my advisor, Dr. Michelle Creech-Ekman, for her guidance, as well as Dr. Chris Haniff from Cambridge for his advice as well as his guidance. And for the use of the ADC tool, I would like to thank Bashar Webb, who is a graduate student at the University of Portugal. If anyone has questions, I would be happy to answer them.
Okay, so I have a question, and you may have covered this. So when the, I'm going to use the word beam, even though I know it's not correct, comes back in through the atmosphere and hits the collector dish.
Mm-hmm.
And then it hits the prism and then the collector dish and then goes through and does its whole thing.
Mm-hmm.
It seems like there's no adjustment for a change in atmosphere. So does our atmosphere change over, it's going to be looking over, atmosphere directly
Mm-hmm.
over Magdalena Ridge, right?
Mm-hmm.
And so, but I'm assuming that atmosphere isn't stagnant. It changes and makes a difference. So will that prism collection system be able to adjust for the change in atmosphere too? Or is it just you figured out kind of a broad, this is generally what the atmosphere is going to be, and we're just going to go with this?
So you're absolutely correct. The atmosphere is quite turbulent, and with the change of the seasons, we see different characteristics of the atmosphere. And so there is essentially a bit of you could say a broad solution, kind of looking at the general atmospheric behavior over the year and seeing how it typically behaves, and setting certain thresholds, as well as very small corrections, as you've said, that the atmosphere is always changing. And so these ADCs are actually able to be moved in translational. So if you can see my hands, they can slide laterally. And there are also designs for ADCs in which they rotate in order to effectively mimic the atmospheric turbulence, but you could think of it as mimicking in the opposite magnitude. Hopefully that helps answer your question.
Yeah, it was great. Thank you.
I had a question. So in figure 2, you have all of the light rays coming down towards this the dish. If the dishes are in a parabolic shape, why don't all of the light rays reflect the same point? Like,
so I think this figure is pretty exaggerated as far as the size of the parabolic dish and the the size of the parabolic dish and the distances that we see the light traveling, as well as where it is occurring. So I think maybe the exaggeration of the parabolic size might be misleading. I hope that answers your question a little bit.
Milani, this is Michelle. I had a question.
Hi, Michelle.
Hi. Do you recall how many different glasses were in the catalogs that you looked at, that you tested?
Let's see. So we have 3 catalogs, which are the Schott, O'Hara, and Nikon catalogs, but I do not recall a specific number, so I'm sorry about that.
I'm guessing it's hundreds of glasses, though. Here.
Yes.
Okay.
Yes.
Well, thank you, Milani, for the fascinating presentation.
Thank you.
At this point, I'm going to reintroduce Savannah Bradley, and we will cycle back to her poster on biomimetic and bio-inspired anti-predator drones. So hello again, Savannah.
All right, hello, part 2. Hopefully you guys can hear me better now. Sorry about the internet issues. Socorro internet is not very nice to me. That being said, please let me know if there's some more audio issues, and I will just continue on from there. So just to start over, what my research is looking into is biomimetic and bio-inspired anti-predator drones. Those are a lot of big words, so what does that really mean? My research focuses on drones in the defense industry, and drones in the defense industry have many different applications, looking from military to surveillance to border patrol. And a lot of drones tend to be attacked by other drones to keep whatever airspace it is safe. And so, especially if we're looking at military drones, these drones are attacked by various predators, including other enemy countries and things of that nature. So for the predator mechanisms, there are 4 stages to prey a drone, and these are detection, tracking, targeting, and attacking. Detection can be done by multiple different avenues, including thermal imaging, radar, acoustic sensing, and other detection mechanisms. Once these drones are detected, they will then be tracked, usually using machine learning algorithms to be able to tell which thing in the sky is a drone versus a bird or some other aircraft or animal. Once it is confirmed that this is the drone that they're looking for, then they can attack the drone using various methods. So this research focuses on what can we do to keep our drones safe. What sort of inspiration can we take from animals in order to avoid detection, avoid being attacked, or being able to carry out our mission once the drone is attacked. And if you look at the upper section of the middle panel here, I've researched a lot of different anti-predator mechanisms in animals. 2 examples can be shown here. On the left is looking at how birds actually molt their feathers to make sure that they have the strongest feathers possible. The keratin in birds' feathers tends to decrease over time, and so this keratin is actually what increases the strength in their feathers and in their wings overall. So from time to time, usually around there's one period over the year that birds will tend to molt their feathers and grow new ones in order to keep their strength and be able to continue their flight. And then on the right-hand side, there's an image of a lizard that is blending in with some leaves. This is a really common anti-predator mechanism in animals. Camouflage, most people think of chameleons or octopus, but many animals exhibit some sort of camouflage mechanisms in order to stay safe from predators. So after researching these different mechanisms in animals, we can look into how can we take these mechanisms and put it into our drone technology or our aerospace technology as a whole. So the lower part of this panel shows some bio-inspired concepts that are taken directly from animals. For example, looking at table 1, we have escaping, which we can code our drones to become maneuverable when a predator is near. There's also autotomy, which has been my main focus in this research overall, where we can look at animals like lizards who get rid of their tail once a predator has grabbed onto it in order to stay safe. A larger image of how we can take inspiration of this can be seen on the lower left-hand panel, and this is looking at a schematic for a proposed concept of a drone with sacrificing wing sections. So this is very similar to how lizards would get rid of their tails. However, in this case, once a wing section is damaged, the drone would drop that wing section and drop the exact same amount of wing on the opposite side in order to keep the stability and the aerodynamic efficiency. This allows the drone to continue its mission and finish its flight even without those wing sections. The one caveat to that is that once it's dropping its wing sections, it loses lift, but it loses lift, but it also loses drag. And so with that, it can continue its mission, but it doesn't have as much endurance. So that's one thing to keep in mind. Going back to table 1, there's multiple different ways we can utilize camouflage. For example, using projectors on the top of our drones that project on the bottom whatever is above it to essentially make it invisible. There's also a Teflon coating that becomes reflective, so it makes it hard to detect those drones. And the other method that I've been researching is e-ink panels, which I don't have an image on this poster, but e-ink panels are panels where there's 2 different colors. For example, we could have, for this application, black and blue, and the more positive current you put in would give more of a blue color, and the more negative current you put in would give a higher black color. And this would allow us to essentially match the color of the surrounding sky. And lastly, another proposed mechanism is playing dead, where a drone simply just falls to act like it's already been attacked. This is a much more primitive concept, as it essentially loses the capability of the drone to complete its mission. These are all proposed concepts that are currently being further researched further and being looked into. Like I said, my main focus at this present moment has been the sacrificing wing section drone. And so how do we create these types of drones? If you look at figure 4 on the right-hand side, it's a little hard to see in this format, but this is the design process for a fixed wing drone. So this is the flow chart of the process we would go through in order to design a drone that would be able to sacrifice wing sections. With that, my apologies again for the internet issues. If anyone has any questions, please feel free to let me know.
Thank you, Savannah. I just have a minor clarification question. In the bio-inspired concept section where you have the micro UAV to MAV UAV, what do these acronyms stand for?
Oh, yes. Thank you. I definitely should have made that a little more clear. So if we're looking at the different types of drones, or UAVs as they're typically called, UAV stands for unmanned aerial vehicle. And there are different sizes. So there's essentially a spectrum of sizes, and these different acronyms show those different sizes. So a UAV is an unmanned aerial vehicle, which is the large military drones like the Predator drone that a lot of us know. But then there is the micro UAV, or the micro unmanned aerial vehicle, which is a lot smaller, and the which is a lot smaller, and it's more of the size of a typical like quad rotor hobby drone that you can buy at like a hobby shop. I also saw a question in the chat. So have you been able to construct a drone that is able to drop off sections and still fly? At this present moment, we have not completed the construction of that drone. If you're interested, I'd be happy to share a follow-up paper on this research that is specifically on the drone for discarding damaged wing sections. At this present moment, what I've worked with Dr. Hassanalian to design is a drone which uses an integrated sensor network on the top of its airfoil, which essentially tells the brain or the center of the drone when a section has been damaged. And once it's aware that it's been damaged, it uses linear actuation. So that essentially just comes that just screws into the middle section and just drops the wing section simultaneously. This is still in a concept stage. It is yet to be manufactured. Something like a countermeasure, which has perhaps a couple of these specifically set to release with the idea that the drone may continue to fulfill the mission. Yeah, so Dr. Cox, I'm trying to understand your question a little bit.
What I was thinking, Savannah, is that oftentimes when you're building a drone, you might have countermeasures in it that are able to be dropped off at an appropriate moment so that that could get destroyed. And the rest of the system is able to continue on. So it's an intentional drop.
Yes.
Go ahead.
Yes, so exactly. That's like I said, this has been the concept that I have been pursuing most of my research on. And we've looked at two methods, like I said, the integrated sensor network, where it's essentially just one big drone that can drop certain sections. But the other that I've looked at is using swarming drones. And what this means is that it's multiple small fixed wing drones that are put together, and then they can do exactly what you're saying. They can drop off when necessary to sacrifice themselves for the sake of the mission.
Okay, well, thank you, Savannah. Excellent presentation on drones. We're going to move on to our next presenter, who is Teresa Trujillo. And the title of her poster is Effect of Surfactant on Saline Water Evaporation and Crystallization.
Hi, everyone. I'm Teresa. I'm working in the chemical engineering department with Dr. Chattery on this project. And so Why is this really important? So freshwater scarcity is actually an ongoing problem that's still being faced due to increasing urbanization in a lot of areas. So treatments of produced water, like from the petroleum and mining industry, can actually help regain a lot of that fresh water back, as well as produce a marketable salt or crystal that can provide profit for the company. Some traditional treatment methods like reverse osmosis are typically used, but they're inefficient because the membranes used in them tend to foul really easily because there's a lot of salt in these solutions. And then you're left with a higher concentration salt brine. And then what do you do with that? Another method is desalination ponds. And some desalination ponds do have a water recollection system. But again, these are inefficient because they require a large area of land, and that can be quite expensive. And if you don't have a lot of solar light regularly throughout the year, you're not getting a lot of evaporation from that. So what I'm looking into is how you can add surfactants or surface active agents into solution and actually increase the evaporation. So surfactants are molecules that contain a hydrocarbon hydrophobic tail group that you can see here in figure 1, as well as a hydrophilic head group that normally contains a charge. And that's how we characterize what kind of surfactants we're using. So when you add these types of molecules into solution, it can actually reduce the surface tension of the overall solution, and that is thermodynamically linked to the latent heat of vaporization. So we could potentially get an increased evaporation rate by adding these into water. A couple of issues currently right now that I'm still working on is that because it accumulates on the surface, that's where it likes to be to reduce hydrophobic contact, it decreases the effective surface area for water to evaporate from. So basically we're evaporating all this water and it's got nowhere to go because there's surfactant molecules on the surface instead. Another issue is at high concentrations, the hydrophobic tails don't have surface to go to, so they start attaching to each other. And it forms micelles in solution, which is basically like a spherical ball that just looks like the hydrophilic, heads that are on the surface in contact with water. So with all of that kind of initial background, what did I really do? I tested some salt water, which is just pure sodium chloride table salt. And then I added 2 concentrations of surfactants. I added 1 ppm and 370 ppm. I tested both of these concentrations with exposing them to solar light, so under a solar simulator in the lab. For this one, I used 20 milliliters of solution roughly, and I let it go for 2 hours so that way I got good evaporation. And then to see if thermal evaporation would be similar, I heated 4 milliliters, a smaller sample size, in a dry bath, and I let that go for 1 hour. So the results that I saw for these experiments is that evaporation rate wasn't really affected much by the addition of surfactants. And I concluded this by the mass measurements that were taken over the duration of the experiment. So under the solar simulator, I took the slope of the line after 30 minutes of evaporation, and there wasn't really a good change in the number that was received. So they were all roughly about 0.026 grams per minute that were lost for all solutions. And in the thermal evaporation experiments, there wasn't a increasing, decreasing trend. The data points were kind of all over the place. So I couldn't really say that evaporation rate was affected significantly. In going to crystallization though, there was a significant change in the formation of crystals from solution. So overall, there was an increase in the mass obtained of crystals from solution. So for the saturated sodium chloride solution, I received about 1.6 grams of crystals, but with the addition of CTAC at the high concentration, I could receive 1.9 grams of crystals. So roughly 0.3 gram increase. Another thing that was interesting to see was that the size of crystals is actually decreased. So in figure 3, you can see that the image of the crystals. So the very top one is the crystals that came from the saturated sodium chloride solution with no surfactant. The second figure, figure B, is with 1 ppm surfactant, and the last figure C is for 370 ppm surfactant. So you can see they're obviously much smaller. The first set of crystals is a little bit over 1 millimeter in length, whereas all the other crystals with the presence of CTAC are much smaller than 1 millimeter. And all these findings were confirmed with the thermal evaporation data as well. And the most interesting thing that I found actually was that the amount of time that it took for me to see salt in solution from a microscope was actually decreased. So initially, with just a salt solution with no surfactant, it takes roughly 15 minutes to see crystals. When you add 1 ppm CTAC into solution, it takes 8 minutes. And when you add 370 ppm CTAC, it only takes 5 minutes. So that's very interesting. And reasons why I'm thinking I'm seeing these findings. So for talking about evaporation rate, when you add surfactant into the solution, it tends to accumulate on the surface. I've already mentioned that. And so because of that, it's not really interacting with the water molecules. And so the attraction between two water molecules remains the same. And so there's no increase in evaporation rate that can be seen. It could also be due to the fact that the water is trapped because of surfactant on the surface. But that seems negligible at this point because it's hard to get equal forces that oppose each other in terms of evaporation rate and then effective surface area loss. For the crystal growth, the reason we see decreased size is that the surfactant, in order to reduce, once again, its hydrophobic contact, it attaches itself, it absorbs itself onto the crystal surface, and it stops growth of the crystal at that point. So instead of getting bigger and bigger crystals forming, you get smaller crystals, and then the solution can make more salt crystals forming from the solution because the supersaturation is changing. This could also be why we see more crystals in solution compared to the saturated salt solution that control that I tested. Another reason could be that at high concentrations, these micelles that I mentioned could be acting as nucleation sites for salts. So that's when the salt ions form around the surfactant micelle and they begin to form solid around them. And that's more energetically favorable. So it's more likely to occur in solution rather than just having all these ions come together, hopefully, and make volume out of water, solid volume out of water. And in terms of the increase in time taken to see crystals, there's not a lot of research about it. So when you try to look into this effect, you see that the nucleation kinetics are always held constant when making particles from solution. And so there's not a whole lot going on in terms of finding out what the effect of surfactant is on nucleation kinetics. So that's kind of the bulk of my research. And in moving forward, I plan on focusing more on crystallization and trying to understand the mechanisms that reduce the time taken to see crystals, as well as the absorption of surfactants onto the crystal surface that affect growth rate. Sorry, that was a lot of information at once, but I'm willing to take any questions if you have any.
Thank you, Teresa. I guess I'm trying to get a bigger picture understanding of the different techniques that say a water treating company would use to try and separate out these solids. So besides that, your idea was that surfactants could speed it up, make it less energy intensive, more cost effective. What other avenues of exploration are there for reducing the energy needs or the cost of extracting solids?
So there's a lot of research onto photothermal materials, and those are just materials that absorb a large amount of incident solar light and convert it into heat. And they're working into making those more cost efficient as well. There are some metal nanoparticles that can be used, but they're subject to a lot of fouling and they're kind of expensive to fabricate. There's a lot of research going on into carbon-based materials. So parallelly, another researcher in my department is looking at surface carbonized bamboo as a way to put it basically on the surface of the ponds and use that as a photothermal material. And because bamboo grows readily anywhere, actually, it's an abundant resource that can be used.
Thank you. I've definitely seen, or go ahead. I think there's another question just as I spoke up. Or perhaps not. I can definitely attest to bamboo's rapid reproduction. I've seen yards overtaken by bamboo in my native Indiana. So thank you, Teresa, for the fascinating presentation.
Thank you.
Our next presenter is Janine Haying Melendres, and the title of her poster is Investigations of Ozone Dynamics and Chemistry from Balloon Sounding Data.
So we're just going to pull up her PowerPoint. She had slides she wanted to show. So 1 second. 152.
So good morning, everyone, and thank you for your patience. Yes, we will be doing a little bit of a PowerPoint presentation because these plots that I have produced are very, very small. And in order for me to say anything, it'd be helpful to actually see them. So yes, I'm Janine Haying Melendres from the physics department, and I will be talking about a project that I started last fall called the investigation of ozone dynamics and chemistry from balloon sounding data. So to start off, to give a little background, we would like to know, well, why is ozone important? And it's important for two main reasons. The first is because ozone protects us from the UV light that comes from the sun, which can harm us. So skin cancer is very prominent in today's today's problems, and and it also harms plants, animals, you name it. And secondly, ozone is also a strong greenhouse gas. And so, but it also depends where the ozone is located. So if we go to the figure number 1, the IPCC, or they're called the International Panel on Climate Change, they quantify the effect of gases on our climate. And so this is called climate forcing. And so here in this figure, we have a couple of greenhouse gases. And then at the very end, we have tropospheric ozone and stratospheric ozone. So a positive climate forcing is equivalent to a surface cooling, while a negative climate forcing leads to a surface warming. So in this figure, we can see that tropospheric ozone is tropospheric ozone is positive and stratospheric ozone is negative. So this kind of tells us, like the ozone in the troposphere it leads to a surface warming, and the stratospheric ozone leads to a surface cooling. And going back to the main poster, so the methods that I used for this project included a package made by students here at Tech called Rio Sol, and we also used two National Oceanic and Atmospheric Administration locations. They launched balloon-borne instruments called ozone sondes that track temperature, humidity, and so forth. And so we compiled data from the two NOAA locations into International Data Language, or IDL, to kind of do more analysis on what each balloon sounding tracked. And so just a note, there are more than one NOAA locations. However, for the time being, we just focused on the two, which are located in the map in the second figure, yes. And for the results, so once we did some analysis, we produced 4 sets of plots. And when I say we, I meant me, but we produced 4 sets of plots with 4 plots in each set. So just to clarify, we have Boulder on the right column and Pago Pago, American Samoa on the right column. Then the top of the top row of the 4 plots corresponds to January 31st, 2003, and the bottom row corresponds to July 8th, 2003. So if we go to the first set, we have the temperature with varying altitude. So in these plots, we can see that the temperature decreases as you go up in altitude up until you hit the stratosphere, then the temperature goes up. We also see a lot of wiggles, which is important to us specifically because it tells us a lot of different behaviors varying day by day. So, and then another thing to know is that the coldest point, so when the balloon is between the troposphere and the stratosphere, we hit the coldest point, which is called the tropopause. And this is also, again, another important thing to us because so in these 4 plots, we can see that normally the tropopause is found higher up in altitude in summer. In summer at Boulder, and then at Pago Pago, Samoa, we see nominally less seasonal variability. Going to the next 4 plots. So when we have a measure of pressure and temperature, we can calculate a quantity called potential temperature. And so from these 4 plots, we can see that the tropopause is actually higher at Pago Pago, Samoa in general. And then there is also a bigger seasonal difference in at Boulder, excuse me. One thing to note is, so the red lines are actually the measurement, and then, the black line is the measurement, the red line is the smooth fit that we call, and we do this just to see the differences, more or less the wiggles we want to notice when these 2 quantities vary. Moving on to the next plot, we have the ozone mixing ratio. And so from these red and black lines, we see the same exact thing as before. There's a lot of wiggles. And then another thing we can see is that the ozone is 100 times more in the stratosphere. And so in order to see these differences, we also used a log scale for the ozone so that it would become more apparent to us. And again, lots of wiggles, we love that, which can tell us a lot about the different the temperatures and how the ozone is varying as we go up in altitude. And then going to the last set of plots, we have the total ozone lamina detection. So again, there's not enough time for me to explain every little detail, so please bear with me, but I will try my best to explain the most important things. So in these plots, we have a blue line, which is the ozone anomaly, or the difference between ozone and the smooth ozone. The red line is the potential temperature anomaly, which is, again, the difference between the measured and the smoothed. When we have a correspondence between both the blue and the red line, we categorize that as a gravity wave. So in order to sort of say whether or not we have an ozone lamina, which are just stacks of ozone, either high or low up in the atmosphere. So in order to do that, we look at the light blue dashed line in the middle of the figure. And so when either the red or blue line go above or below it, then we know we have a lamina. And so then we further look to whether or not the red and blue line match in like the way they move up and down. So if they look the same, then we have a gravity wave. And if not, then we categorize them as non-gravity waves. So also the gravity waves are denoted by like red bars on the far right of each plot. And then if there are no gravity waves, they're also shown as orange bars. So going back to our poster, in the future, I will look at more locations and dates to say more about the non-gravity waves and gravity waves in order to also say more about the depletion and production of ozone. Currently, NOAA launches a balloon ozone sonde every week about, also varying within each region. But that means we have over 30 years of balloon soundings that we can import into this algorithm to analyze further. And with that, if anyone has any questions, please feel free to tell me.
Hey, Janine, it's Michael.
Hi.
Good morning. Good afternoon.
Good morning.
So question I have, is there an optimal stacking of ozone that keeps us, I'm making air quotes, safe? You know, is there a particular way that ozone needs to stack in the atmosphere, or the lower atmosphere, I guess, to protect us?
Well, to first clarify, I am very, very new at this, so I couldn't for sure say whether or not there is, but like we saw in the IPCC figure, so anything in the stratosphere is going to protect us from the UV light and the bad ozone, the bad things that we want to keep away from our atmosphere, whereas the tropospheric ozone obviously is not going to protect us. So if we have more ozone stacking in the troposphere, then again, it's not going to protect us, so why do we want it, right? So I hope that kind of
I got you.
answers your question. You're welcome. Oh, we got something in the chat. Let's see. You mentioned that you can analyze the past 30 years of data for future research. Would climate change pose any problem with projecting that data to the future? Potentially. I mean, it just depends on what we find again, and yeah. So kind of how I was explaining to Michael, you know, if we find that we find more variations in the stratosphere, maybe that means that, I mean, it can mean a lot of things. It can mean that that more ozone is being depleted or produced. We don't know. So yeah, it just depends on what we find. And but yes, definitely it could change how we view climate change in the future. And Justin has a question. Hi, Janine. Is there any other uses for the data that you already have? Off of the top of my head, I don't think I can answer that. I mean, we can obviously see differences between days. Like I talked about, seasonality is a big thing. You know, Pago Pago American Samoa is closer to the equator, so it makes sense that there's less of a seasonal variation, because the temperatures and just how it is there is most likely to stay the same year round. Whereas at Boulder, Colorado, we have, you know, very extremes. We have the extreme winters, we have the extreme summers. So we can look at things like that, and yeah. Oh, we can also say more about atmospheric changes. So I know my advisor has done things like this, where he has analyzed data from the balloon soundings and during like a hurricane and stuff like that, and you could see that there are definitely variations within the ozone that we see, and it does change it. I can't tell you off of the top of my head because I wasn't on that project, but I know that definitely you can see different things, like how our ozone is changed depending on weather or any natural disasters such as that.
I'm on mute. I'm now off mute. Thank you for the fascinating presentation. We're going to move on. Our next presenter is Maya Martinez Metzgar, and the title of her poster is Mitochondrial Nuclear Genomic Stoichiometry in Diploid versus Polyploid Snails.
Hi. Oh, okay, we got it. Okay. Okay. Hello, everyone. Today I'm presenting my research studying the mitochondrial to nuclear ratios of genomes in snails and how that's important and why that can be applied to cancer research. So what is polyploidy and why is it important? So polyploidy is, in other words, best described by the figure 1, where there's like it says diploid and polyploid, and the diploid shows that if you look really closely, there's 2 little blue things. I'm not sure if you can see, but they're little chromosomes, and that represents a diploid. A diploid has 2 copies of chromosomes, hence diploid double. A polyploid is the same concept, but depending on what variation of copy numbers you're looking at, there's going to be more than 2. This ranges from tetraploid, triploid, hexaploid, all the above. Where polyploidy came from is what we think is from a whole genome duplication event, which happened very, very long time ago. And a whole genome duplication event, we're still not familiar about the consequences of that situation and what are the consequences for energy production. And in the cytonuclear lab, we're trying to figure out what are the consequences of why that's important, because it's obviously very important because it's present in cells today. And as evolutionary biologists, it's really important to find out the why and where it came from. So in regards to our project, and going from diploid cells to polyploidy cells, so from previous studies, we've known that tumors, they are very abnormal and they're very atypical from what we usually see in human cells or somatic cells. And what makes it different is its genetic makeup, and from the information that we do now know. So here, relating that idea about diploid to polyploidy in different numbers of chromosome copies is regarding to tumors, polyploidy is an uneven distribution of these different numbers of chromosomes. Like, for example, here in figure 2, there are these little different circles, different shapes and colored circles represent the diversity and how the genetics is very different from just any other typical human diploid cell. And so that's what we're trying to study, is how, knowing the fact that cancer is polyploidy and it is not something that we typically see in everyday cell research, we're just trying to figure out, why is it polyploidy? Why is that important? How can we figure out to use polyploidy to our advantage and learn more about the process? So maybe one day we can figure out better therapies for tumor, helping eliminate cancer eventually. But that's very big, but just help understand this very complicated concept as much as we can. So in biology, typically the more simple things come before the more complicated. And before we start jumping into cancer research, we're really trying to focus on these freshwater snails from New Zealand. And these freshwater snails in New Zealand are very small, but however, they are very important and they're very powerful tools of understanding this complicated concept. These snails vary in polyploidy number. As you can see, I'm not sure if you guys are familiar with New Zealand, but there's these little pie graphs in figure 3. And these little pie graphs represent where our snails were collected when we gathered our data, and if like what percentage, if they were diploid, triploid, tetraploid, etc. And using these snails, they're very easy to use and study in the lab. They're easy to sequence. They're easy to look underneath the microscope. And that's why we're really focusing on understanding these snails very well, so we can apply them to somatic cells and into health biology. So here is our procedure. What we ended up doing was we mapped the whole genome sequencing reads to reference genome assembly, which those are some big words, but in figure 4, this shows in a nice visual way the difference between the diploid and nuclear and mitochondrial genomes that were sequenced in our data. And so read depth means the number of times DNA has been read. And when something is read, it means the amount of times the nucleotide or the DNA has been run through the sequencing machine. So, and then the windows, as you can, if you look on the side, right-hand side, it's like a skinny column right next to the big block. That's a window, and it means a chromosome that was divided up into regions, and we're using that to kind of compare our data to. And from gathering our data, we took some means and medians, and we developed our mitochondria to nuclear ratio. Why is the mitochondria to nuclear ratio important? It's important because it helps us relate information gathered from the snails and helps us relate it back to tumor cells, and how we can apply that to humans, and how we can apply the snails' basic, I want to say basic genetics, but relate their genetics to us and how it can be more applied, how we can measure our variables better. And then in figure 4, it's another representation of our data. Figure 5. It's really kind of hard to see, but each colored dot, there's gray, black, and yellow. Those are the different species that we looked at. And those are, in that plot, it represents the replicates of the sequence data. And what we found was using ploidy level to estimate the number of cells. There's approximately about 122 mitochondrial genomes per cell, which is really cool. And it's really interesting that we're able to discover that, and that has implications to help us better understand cancer and how that could fit into that. So from our conclusions and future directions, what we can do is we can now measure mitochondrial DNA using sequencing, which is a really powerful tool, really easy. However, some problems that could be encountered there is the quality of data. And when we were first running through our experiment is we had low quality data and found high quality data. And that really helped us have a go in the better direction of where we want to go regarding to the cancer cell and genetic makeup. We also found that triploids have more mitochondrial DNA per cell than diploids, which is very interesting. And when I first began, I was talking about whole genome duplication events. And this could possibly not, I want to say a reason, but this can help lead us into maybe some possible theories about triploids and mitochondrial DNA from whole genome duplication events. And I'm not sure if I said this before, but whole genome duplication events are not very well understood. So we're dealing with a topic that there's not much information given, and we're doing as much science that we can do at the moment to get closer to finding out why that's important. So looking into the future, I listed in table 1 the different snail lineages among ploidy comparisons from different lakes like Alexandria, and we will be comparing in the future ploidy levels between diploid, tetraploid, and triploidy. And the other polyploid context we're looking to go into is tumors and really understand the metabolics of tumors better, because we know that tumors, they take up a lot of energy. They consume a lot of oxygen and they need a lot of energy, and knowing information and understanding polyploidy well helps us understand why that metabolic system is the way it is and how can we combat that for better treatments in the future. That is my project. Any questions?
I guess, Maya, thank you for the presentation. I'm wondering, how does, like, we have this polyploidy occurring in snails. What happens in, how does snail genome relate to the human genome, I guess? Like
okay. Oh, sorry, I didn't mean to cut you off. You can continue.
I was done.
Oh, okay. So how does polyploidy relate to the human genome? It doesn't necessarily relate to the human genome. I would say it's more related to the cancer tumor genome and why that occurs, because cancer tumors occur because of mutations and over rapid cell production that is just kind of unexplained, which has to do with mutations. And I would say the polyploidy is more from the snails is more related to the genetic makeup of the tumors, not necessarily just human cells as a whole.
Thanks. If there are no further questions, we can give our applause to Maya for the excellent presentation. I will bring our attention to the fact that we're running perilously close to going over time. We have 3 more presentations and we have about 12 more minutes at the moment. I think this is due to some technical difficulties and general enthusiasm from presenters. So at this point, I would like to move on to our next presenter, Jacob Wemhoner. His poster is titled "Towards Physics-Based Modeling of the Lightning Return Stroke."
Hi everyone, I'm Jacob Wemhoner. I am a PhD student in the physics department at New Mexico Tech. And I will be presenting my project titled Towards Physics-Based Modeling of the Lightning Return Stroke. There's a lot of big words there, but the main point is that we need a physics-based model because as the climate gets warmer, lightning becomes more frequent and more severe. And this is a problem because as all of the previous models of lightning have been experimentally based, so based off of empirical data and information that is on the less severe, less frequent lightning strikes in the past 20 or 30 years. So the point of this project is to investigate a model that looks at the lightning return stroke that can properly estimate the values in the lightning return stroke. So I keep saying lightning return stroke. The lightning strike is made up of two parts. It's made up of the leaders, which you can see in figure 1, and the return stroke, which is the brightest, most noticeable, and most impactful part of the lightning strike. It releases about 4.2 gigajoules of energy, which is about 1 ton of TNT's worth into the surrounding environment. And the leaders create this channel that you can see at the very end here. And the lightning strike starts at the ground and goes towards the sky. So all of my other models that you'll see here, they'll start at 0 kilometers and they go towards 2 kilometers. This is because the lightning return stroke starts from the ground and goes and propagates upward to the sky. I'm going to, because the channel is created by the leaders, this effectively makes it a 2 kilometer long wire, and we're going to model the current through the lightning strike as with the telegrapher's equations, which model exactly this, the current in a wire that's just transmitting energy. The 3 models that I looked at to compare analytically were a zero resistance model, a perfect conductor, a constant resistance model, and I used the empirical nonlinear resistance model that was developed that is taken from data. Oops. The video here is the zero resistance model and an analytical solution that is just effectively from the wave equation. The problem with this is there is no attenuation, there's no reduction in the strength of the lightning strike. So there's a lot of issues with the zero resistance model if you wanted to use it as an accurate model of the lightning strike. So this leads me into the other 2 models, the constant resistance model, which has an analytical solution that we can compare to, and a nonlinear resistance model that has no real solution. You can just approximate the solution. So I have all 3 graphed in figure 3 on the right here. And what you can see is the red is the zero resistance model from figure 1. The blue here is a constant resistance model that kind of stretches out over time. And the green is the nonlinear resistance model. I'm approximating all of these models with the finite difference time domain method, which I have listed the step equations for up here. This method is second order accurate in time and first order accurate in space, making it very accurate for an approximation. From what we can tell, the analytical and the model solution are exceptionally close. And so this finite difference time domain method should work to give accurate data and to determine whether or not a fundamental physically based model is realistic when compared to actual data. In figure 4, you can see kind of a summary of all of the models together. This part A is just effectively this movie, but a still picture. Part B demonstrates that the nonlinear resistance model has a much slower much slower velocity than the two other models. In this third graph, you see a cyan line which compares an analytical solution to the constant resistance model, which we didn't get to see because it was taken over by this zero resistance model. So I think that's it. Are there any questions?
I have a question.
Okay.
So how could your model be applied to different scenarios? Like, I don't know, could it be applied to detecting lightning before it happens, or, you know, things like that?
So my model is based on the return stroke. Specifically, a model that would predict lightning before it happens would have to have some solution for the leaders, which you can see again in the figure 1. They're the part that leads up to the actual strike. That's based more in statistical mechanics. The thing that you can do with a model of the return stroke is take information from, say, NASA's geostationary lightning mapper, and determine exactly how much energy was released into the surrounding. Instead of having an approximate, you can determine which lightning strikes are going to be after they happen. You can get instantaneous data about whether or not they were exceptionally harmful to the environment.
Cool, thank you.
Well, thank you, Jacob. Thank you for the excellent presentation. Our next presenter is John Huckabee, and the title of his poster is Influence of Particle Size and Fabrication Parameters on Luminescence Properties of Zinc Sulfide, Copper, and Aluminum Phosphors.
Hello, my name is John Huckabee, and this is a project we did in conjunction with NASA's EPSCoR program with the Mechanical Engineering Department as well. And the ultimate goal of the project is to create an elastical mechanoluminescence composite. And so that's just mechanoluminescence is the ability of a material to emit light with the application of mechanical stress. And elastical mechanoluminescence is the ability to do so in the elastic strain range of the material, meaning that all of the deformation put into the material is recoverable and not permanent, so that the behavior can be repeated. So my part of this project is synthesizing the powders, the zinc sulfide powders that are to be used. And so these are co-precipitated copper and aluminum doped zinc sulfide phosphors. And we started our procedure by with the co-precipitation procedure, and that occurred in ethanol with ammonium sulfide as a sulfur source. And afterwards, we with the zinc sulfide particles with a small doping of copper and aluminum, we milled that powder in a planetary ball mill while adding a little bit of sulfur, and then we put it in the furnace for 800 degrees C and annealed it. And so these are the things that we varied in this procedure were first the amount of aluminum and copper ions that we added. We also varied the amount of speed, duration, and rest time between the repetitions of milling so that we could test the effects of milling energy on the final size of the phosphors. And we also changed the amount of sulfur powder that we added during this time. And we also investigated some commercial copper doped zinc sulfide powders that we used to look at the effects that our milling procedure would have on those powders. So the first figure that you see here is from going from right to left, the first figure is just our setup, our milling setup on the left. That's a planetary ball mill, which planetary just describes the motion. It spins as it's going around a central axis. And then we baked annealed our powder in a carbon atmosphere. Those are carbon granules surrounding an inner crucible. And so some of the things that we did to characterize these powders were we used a Raman spectrometer to reveal the fluorescence response of the material. And we also took some scanning electron microscope images so that we could look at the the particle size. And so as you can see on figure 3 here, it shows basically the same thing that you see in figure 2, which is that by adding more sulfur powder during the milling process, we get significantly higher fluorescence in the sample, and that's across different ion concentrations, so different amounts of copper and aluminum in the zinc sulfide. And these two pictures that we have in the third column, they are zinc sulfide powders with different milling energies used on them. So the upper one has a higher milling energy, and the lower one has a lower milling energy. So you can tell from this, it's a little bit harder to make out on the upper one because the particle size is smaller, and we're at the resolution limits of the STM that I was working with. So, but those ones are less than 100 nanometers in diameter, those particles, and the ones in the lower picture are about 300 nanometers. So we are able to, by changing the grinding process, the ball milling process, successfully affect the particle size of these phosphors. And by increasing the particle size, we can increase the fluorescence response. We also have that data as well. And on the right side over here, something else that we were able to see was that we can change the peak location, the wavelength of the light emitted by commercial zinc sulfide powders by milling them. So we actually can shorten the wavelength of the light by reducing the particle size. This is the quantum confinement effect, which is known in zinc sulfide powders, which we were able to observe. So for future work, it is going to be incorporating, further improving the fluorescence of these powders, and then translating that into mechanoluminescence by incorporating it into a PDMS composite. And PDMS is basically a silicone, what is colloquially known as a silicone. And we have further characterization and further syntheses to do of these powders. And that's about it. I can open up the floor to questions now if anybody has any.
Okay, I got a bit lost there when you were talking about particle size versus, did you say the smaller the particle size, the shorter the wavelength?
Yes, so for the, yeah, that's exactly right. By reducing the particle size, we shorten the wavelength, and this is the quantum confinement effect.
Okay. Cool.
Thank you, John. Just a quick question about sort of what are the practical applications? What are some cases where we would want to have this, to be able to see the stress that a material is undergoing via its luminescence?
Yeah, so there are tons of applications. To name a couple, so in situ, in place stress monitoring of structural things, that can be a big use for them. There's a paper recently put out where they made this composite, the mechanoluminescent composite, and they sandwiched it between other layers of laminates, and then they did handwriting analysis by having people write on top of it and having a camera capture the light emission. So there are a lot of different possible applications for a composite like this.
Well, thank you for the excellent presentation. I would like now to move on to our final presenter. We have Kelsey Romero, and the title of her poster is Private Well Installation Trends and Correlation of Borehole Stratigraphy with Groundwater Arsenic Contamination in Kandal Province, Cambodia.
Hey everybody.
So as previously mentioned, my name is Kelsey, and today I am presenting research correlating sediment color to arsenic contamination. I'll first begin with talking about the data. So the data utilized is from an arsenic contaminated area of Cambodia, where arsenic contamination can be anywhere to 100 times the drinking water quality standards. As for the goal of my research, the goal is to evaluate a data set of sediment cores, and this data set contains data such as sediment color and texture. And we use these parameters to identify where arsenic contamination would either be high or low. So in short, by utilizing the data from 80 well logs, we concluded that of the sediment colors present, gray and red sands are the primary sediment type present in the well screened interval. So just for background context, the screen interval of a well is the area at the bottom of the well which the water is filtered through, for background. And the data can be seen in the pie chart, which displays the colors per well. We also concluded that the average depth of each colored sand is qualitatively linked to an inflection point in where the proportion of arsenic contaminated wells increases in the total provincial data set. This can be seen in figures 4 and 6. As for future work, we would conduct a more quantitative assessment of the spatial distribution of sediment and arsenic contamination, and in this data, we would include 500 wells. We could also see if our analysis of correlating sediment color to arsenic contamination could be extended to other contaminants such as manganese. And in the end, the primary goal would be to aid in the ability to better predict arsenic contamination in the province. Are there any questions?
So when you're analyzing or when these wells are being dug originally, is there any way to avoid these particular sediments, you know, changes in water table heights, different things like that? Is there any way to actually get water without having to go through these particular arsenic heavy sediments?
So as of the moment, no. There is a drinking water quality index data set that can tell you where previous wells were dug and what the water quality is. And so you could avoid those areas by then, but part of our future research would be able to figure out the stratigraphic sequence of these sands in the area, which would help aid the public from avoiding those areas. So possibly in the future.
And we have another question in the chat, Kelsey.
All right. So how is arsenic so abundant in this area? So the arsenic is coming in through the water, and part of the reason is the fact that there's a lot of rice fields in the area. And this all ties into the agriculture in the area, the water quality, and the type of sand that is present. So, for example, our prominent sands are gray and red, and this has to do with the redox state of the sand. And so if the sand is orange or red, then that would mean that it's oxidized and it's going to be low in arsenic. However, if it's gray, then it's reduced, and gray sands contain a lot of iron oxides in them, and the arsenic coming in through the water is going to attach itself to those iron oxides. Yes.
So basically, it's just all this arsenic is just a confluence of situations that's causing all this to show up, right?
Yes, it's just a byproduct of the agriculture and the water that's being filtered through the area. Yes, arsenic is naturally occurring.
Well, thank you, Kelsey, for the excellent presentation. And at this point, we've come to the end of our presenters. So a big round of applause, virtual applause, for everyone who has participated in this poster session. At this point, I would like to pass it over to Dr. Cox for the closing remark, for some closing remarks.
Hello, everyone. We thank you so much for attending today's session. Once more, we'd like to thank Dr. Johnson and Ms. Lyons and the student presenters and all the SRS staff that are a part of this program. Now, in the chat box, we placed a link to the poster evaluation form. And please fill out as many as you can and as many as you're comfortable with filling out. And we also hope that you will consider attending some of the other events at the SRS this year. And you can see that today we have the Computer Science and Engineering Department Showcase occurring, and the 3-minute speech competition, which is always kind of a fun situation to observe because it's trying to remind us of what it's like to give an elevator speech and how we can make our research be clear and presented well. Thanks again for attending, and stay safe.